All right. Hi, everyone. I hope you all are having a great day. My name is Alper. I'm the Education Content Manager for this year's CodeDay Labs. I'm happy to welcome Henny Ben Amor. He is an assistant professor at Arizona State University, and he will be talking to you guys about robot learning, AI, and robotics in general today. So Henny, if you'd like to introduce yourself a little more and get started, that would be great.
Absolutely. Thank you so much, Alper, for the kind invitation, and thank you all for coming today. It's a great pleasure to be here, and I think it's going to be a wild and interesting ride. So let's jump right into it. So about this lecture, so the main goal is not to educate you. It's really to get you excited about robot learning. And my actual objective is to convince you that this is the coolest thing out there in science right now. But at the same time, I want to show you both the what, meaning what is robot learning? What do we mean by that? But also a little bit of the how, kind of how do we get started with this? Kind of at least kind of a rough start. Yeah? Obviously, only kind of 3 smaller lectures would not be enough for this, but I hope I can get you at least through the door. Yeah? And yeah, maybe kind of that will lead you to your first own experiment, and then who knows, maybe a big career in machine learning for robotics. Okay, so maybe a little bit about myself. I'm German. I got my master's degree in Germany at the University of Koblenz. And then I did my PhD between 2 countries, between Germany and Japan. So I was also at the University of Osaka in Japan. And there I did some Android robotics. We'll talk about that a little bit later. And then I went back to Germany for a postdoc. And since 2013, I've been in the US, first at Georgia Tech, and now at Arizona State University, where I'm an assistant professor. And well, what do? I do all sorts of really interesting things. Everything that's related to humans and robots working and learning together. So what you see here is different pictures from the past. Well, some of these pictures, for example, the one here on the left, there I still had hair. That was back in Japan when I was at the University of Osaka doing my PhD. And that lady there in the middle is, by the way, is not a robot. That is not a human being, that's a robot. Yeah, that's what I meant earlier with Android robotics, robots that look, feel, and behave like humans. So just generally, I'm interested in motor skill learning. How can robots learn to adapt to an environment, especially if that environment also includes humans? So what we like to have is, for example, for a robot barista or chef to prepare dinner for you, but at the same time, know when and how to engage in an interaction with you, and when to, for example, hand over a plate, or maybe when to step back and let you have your conversation. So at a high level, that's what I'm doing. And so now let's get started with robot learning. Well, for that, we need to take a step back. For that, we need to really understand what's the current state of robotics, especially industrial robots. So they've been around for quite a while now. So some of the first industrial robots have been introduced in the 1950s. And here we see some of the later or more current versions of these robots, current manifestations. And so in this particular case, it's a plant from Tesla. And these robots are great, but they have some severe limitations. What we'd like to do is to work on the next generation of robots. Robots like, for example, a robot like this, that actually kind of looks very human-like. It doesn't have to look human-like, by the way. But in this case, it happens to look very human-like. And then in order for it to convince you that it's human-like, it also needs to behave that way. And so again, this was at the University of Osaka. So what do we mean by next generation robots? So if we contrast them to industrial robots that we saw earlier. Industrial robots work in structured environments, meaning not only do we have the robot, we also have a conveyor belt that kind of nicely brings the objects to the robot. So rather than having a robot working in an unstructured environment, for example, having a robot that just goes to a heap of objects and then stops picking them, you kind of need to create some device that gets the object to the robot first. And so that's what we mean by structured environments, like kind of any sort of manufacturing plant that you can design and create in such a way that it actually helps the robot. Whereas human environments are unstructured. So you have maybe kind of, for example, right now I'm in North Africa, Tunisia, and in Tunisia we have a lot of sand. And so walking on sand is not necessarily exactly the same thing as walking on kind of paved ground. So another aspect with these industrial robots is that they're kind of static in position and task, meaning they always do the same thing again and again. And that leads us to the next aspect. You kind of have to program them for the task at hand. So if something new happens, for example, the object at the conveyor belt topples over, and you didn't program that the robot with a specific program can grasp an object that is toppled over or kind of put it back in place, well, then the robot will have no way of doing that. It won't even have a way of realizing that something has toppled over. So what we want to have in next generation robots is the ability to, on one hand, navigate and be mobile, but at the same time be adaptive to changes. If something changes, they need to be adaptive to that. And part of this is also being dexterous, meaning kind of being able to use their hands really nicely. Yeah? Beyond just motion, we want these robots to have really high level of vision capabilities. Current industrial robots are very limited with the visual capabilities. And well, what we would like to have with next generation robots is for them to safely interact with humans and their environment. And so that brings us to the big vision of robot learning. So traditionally, we have the following setup in robotics. We have, on one hand, the robot. We see the robot here on the left side. And then we have, on the other hand, the environment. This could be humans, like a child. This could be objects, like a cup to be grasped, and so on, or a hammer to be used. And normally, it's your job as the programmer, as an expert in the field, to sit down and create programs and think ahead. What are all the things that the robot will need, all the skills, and then sit down and write programs that do that. That's not easy. It's very hard. You need an advanced degree. It's very time consuming. You need expert knowledge in many, many different fields, and kind of motion, vision, sound, and so on. And what's most complex is you have to foresee and predict everything that can happen. So again, if something were to topple over, you have to predict, oh, that could actually happen. And whenever you have humans in the environment, it's actually nearly impossible to predict everything that can occur. And so this is where machine learning steps in. What we would like to do is to remove the middleman, remove the programmer, the expert, and replace that by machine learning, which means rather than having a human provide this expert knowledge, we have the robot adapt automatically to, again, the environment or to human interaction partners. So machine learning should make the robot adaptive and really self-reliant. And as a result of that, autonomous. Okay, now that's the goal. Why can't we just go out there and do that? Well, there are a lot of challenges, and I'm actually having here only a non-exhaustive kind of a small list of things that can go wrong. So one of the issues with learning, and we'll see that later, is learning is an iterative process. When we as humans, for example, learn, for example, you're trying to learn how to ride a bicycle. Maybe the first couple of times you're not that good at it. And then after a while, you kind of get the hang of it, and then kind of you understand how to do it. Unfortunately, for robots, it can be really, really challenging. It takes a lot of times, like thousands and millions of trials, whereas humans can learn rather quickly. And additionally, this process of learning has to be automated. I'll give you an example. So I tried to teach a robot, for example, how to pick up a ball and throw it into the hoop, basically playing basketball. And then whenever the robot picked up the ball and threw it, tried to get into the hoop, well, in the beginning, it didn't get into the hoop. And then the object, kind of the ball, was somewhere, and we needed a human to bring it back to the robot. And of course, you can't just have a human sitting next to a robot bringing back the ball whenever the robot fails at throwing it correctly. Another thing we have in robotics is wear and tear, meaning if you actuate the robot again and again, it's actually going to have different characteristics, different properties from the beginning. It's just the motors are going to wear out, and the same thing for sensors. So what some people do then, in order to avoid all of this, is to use simulation. You can use some like video game type of environment to train your robot in the environment, and then just download that module or policy onto a real world robot and hope, kind of fingers crossed, that it works. Unfortunately, the fingers crossed never really works. And in most cases, what you get in simulation cannot be transferred to to the real world. And there's a bunch of other things. I don't really need to go too much into the detail. So just believe me, it's hard. And I've been doing this for 20 years. Okay, so now that we've realized it's hard, let's try to understand it a little bit at a deeper level. What do we mean by robot learning exactly? And the thing I'd like to tell you and kind of really focus on is that robot learning can mean different things. It can have different manifestations. So if someone tries to teach you, oh, let me teach you robot learning, and it's like this specific thing, like, I don't know, reinforcement learning or whatever it is, they're probably lying to you. They don't really understand what they're doing. Robot learning really has many, many different manifestations. And so I'll be talking about some of these today. So, and I'll be giving specific examples, how we can use machine learning to learn control, meaning how we can have the robot move its own body, how we can use machine learning to estimate the state of the robot, how we can use it for estimating and understanding metrics and conditions, how we can use it for perception, so vision, and a bunch of other things. I'm most excited about morphologies, and I really hope that we get to that today. It's basically how we can use machine learning to change the shape of the robot. And you will see some of the most hilarious videos in all of robotics and machine learning later on in the talk. Okay, so just stick around until we get to the hilarious videos. Okay, let's start with learning to control, which is what most people actually kind of understand or relate to when they think about robot learning. So when we try to use machine learning for control, typically we have one of two goals. Either we want to learn a policy, what's called a control policy, or we want to learn an internal model. So let me just explain these two concepts in more detail. And by the way, you can forget all of the math here, but just kind of bear with me. I'm just kind of writing the math for completeness sake, for some of the people here that kind of want that, but you don't really need that to understand it. So what do we mean by learning a policy? Here we see a picture of a very specific task that many roboticists use at the beginning to kind of teach robotics and control. So what you see here is a cart pole problem. So you have this cart, so kind of what you see there, the gray thing with the two black wheels, that's a cart that can be moved to the left or right. So you can move it to the left or right. And then there's a pole on top of it. And you want to move the cart to the left and right so as to stabilize the pole and not have it fall down. Okay, so that's a very common control problem. And now, in order to define how to do this and solve this problem, we need to understand what are the elements of it. So one of the things that we need to solve this problem, to stabilize the pole, is the state of the system, here denoted by X. The state of the system basically just tells us, well, what's the current state of the system or the world? In the case of the cart pole, the state is going to be this angle, kind of whether how upright the pole is, the angle theta. And then in addition to that, we're going to store also the angular velocity. That dot that you see there, that typically means velocity. Okay. So what we have is the angular velocity, kind of how quickly we're making changes in the angle. And then the same thing for P and P dot. P is the position. Where is my cart pole on the floor? Is it already a lot to the left or to the right? And P dot is the velocity, kind of the velocity of the cart pole. So we have the velocity of the pole itself, and we have the velocity of the cart. And what we'd like to have is to have something, and that's called the policy, by the way, that's something or some function that gives us back the best action to perform at every state. So again, what we have is the state of the system. We have the action to execute. Oh, let me see here if I can actually, oh, there's already a question. So I'll be answering some of these questions later on. And let me just kind of see here if I can annotate is actually the wrong thing. I don't want to annotate. No, I don't need that. Is there something? No, I don't see that. So there's this thing normally where you can see my mouse really nicely. But anyhow, so the state of the system is the angle and the angular velocity and the position. The action is whether we should be moving to the left or moving to the right. And the policy is a function that takes in the current state x. So policy pi here takes in the current state x and basically spits out what's the best action. Now, traditionally, in order for you to find such a policy, you need to really heavily understand mathematics and really think about it. Okay, if the angle is like this, then the function needs to calculate the derivative of this and this and this and this. Well, some people are good at that. And there are books, for example, on ordinary differential equations that tell you how to create such a function. So again, what we're trying to find is a function. So let me just annotate this, is a function pi, yeah, that takes in the current state x and gives us back the best action. Yeah? And the current state x exact in our case could be some specific angle, let's say, I don't know, 20 degrees or something of the current pole. Okay, so let me just clear all of this. Yeah? So traditionally, you would read this book and you try to find such a function, but yeah, it's really hard to find. And so now in robot learning for policies, we try to automatically find these functions. We try to kind of search in the space of all possible things, all possible functions, and then try to find a function that actually solves the task. And you can see that here in action. So here we have again the card pole problem, and the pole is basically kind of showing downwards right now, and we're moving the card to the left or right, and we're trying to swing it up and then balance it. And in the beginning, the robot is trying out just random actions, just random stuff. But every time it's doing that, it's trying to figure out what's the best function I can actually apply here to balance this thing, kind of get it upright. And so after a couple of seconds, it tries something else. So it's still failing. After a couple more seconds, it overswings. And then, well, eventually it gets really good at this. Eventually, it tries out some function, and it's stabilizing it. But then you can continue and try to find a way to stabilize it in such a way that it's even robust against external perturbation. So even when people try to touch it, so that's what we're going to see next here. Even when people are trying to touch it, so we're going to see a human kind of come in. Yeah, so we're going to see a human come in and touch it, and it still nicely stabilizes. So the difference was that in this case, the robot was autonomously trying out stuff and trying to figure out which one of the functions and all of the functions that I have at my disposal would actually get me to the goal, which is stabilizing. Yeah? So we didn't have a human kind of sit down and write these functions. The robot was trying them out by itself. Here's the same thing with a small twist. So in this case, we're trying to teach the robot how to balance or kind of create pancake and kind of flip it around. But in this case, we maybe provide an example in the beginning. We show the robot how such a function could look like, how such a motion could look like. Well, if the robot just tries to imitate it immediately, it doesn't really look nice. It kind of, something is missing because the stabilizing forces of the human are missing. But the robot can try again and again. And you can see that here, it's getting better. And it tries again and again to find the variant of the motion that allows it to kind of flip the pancake and still get it inside, inside the, what's it called, the frying pan. Okay, so this is kind of the most famous example for this. So kind of learning policies. So here's something from my own lab back in the days. So the same principle again, there is a human providing maybe just an example demonstration of how such a policy could look like. So how such a function, a movement could look like. So this is my student Eric. He teaches the robot how to stand up. And then the robot tries to stand up. But if it just tries to mimic what the human did, you will see something's off. And boop, the robot falls down. So now what we can do is we try to optimize that, change that bit by bit, whether in simulation or in the real world. And actually, you can see here in the beginning when the robot is trying it out again, it actually falls. But after a couple of trials, the robot finds, again, a variant of this function that was demonstrated by the human that allows it to stand up. And then once we have that, we can transfer it to the robot. And then hopefully the robot can reproduce that. And there we go. So we went from a demonstration of a human to the robot to actual robot policy through iteration and through self-learning. So this is the kind of the most famous type of learning, kind of learning policies. But there's something else you can do. You can try learning models. Learning models means that you try to learn how to model the input and output behavior of some aspect of the robot. And I'll give you an example for that. One example, what's called inverse kinematics. So when you're controlling the robot, you don't necessarily control, and by the way, this thing that you see here is my weird attempt at drawing a robot with 3 limbs. So you have like a 3-limbed robot with 2 joints, kind of 1 joint here and 1 joint over there. And we want to get it to goal position. Oh, actually 3 joints, yeah. There are 3 links, 3 joints. We want to get it to goal position. But the problem is we don't know which joint angles do we need to set to get the robot to a goal position. And so that's typically called inverse kinematics. So how do we find the mapping between joint angles and the position where the robot is going to be at the end? Now, traditionally, I'm pretty sure most of you look at this and say, hey, just give me like high school math, linear algebra, I can solve this. Yes, you can solve this, but there's actually a twist to it. Up to 6 degrees of freedom, it's solvable. After 7 degrees of freedom, it's not solvable anymore. There's no unique solution anymore. So you can try out with all of your fancy high school math, it's not going to work. And well, you can still solve it using mathematics, but then you have to make some interesting assumptions. Let's forget about that. Can we solve it differently? So one way to solve it differently that people in computer animation use a lot is what you're going to see here. And the idea is the following. We can just record humans moving and then try to figure out, okay, where was the hand and what was the joint angle of the human, kind of all of the joint angles. And once we have this data from inputs and outputs, we can learn a mapping between them, kind of a function again. And so that's something that computer vision or computer graphics people use a lot. And so with a technique like this, you can then animate an entire character by just moving a single limb. And so the idea is you collect a lot of data from motion capture. Basically, you have a person wearing all of these fancy kind of points and dots on the body. And then you record all of that. And then you try to learn what were the joint angles, kind of what values did the joint angles have whenever the person was at a certain location. And so once you have that, you can now control that person by just controlling kind of the final location where they need to be. So let's go back. So here in this case, they were controlling the entire body of the person, but just controlling the foot. And so there are really interesting applications here, even outside of robotics. And now, kind of, if we stick to robotics, kind of how can we use this? Well, we could use it, for example, to learn how to control a robot that moves like an elephant trunk. Interestingly enough, there are these kind of robots. So a German company called Festo, oops, let's go back, creates one of those robots, and you can see it here. But the thing is, this robot is really, really hard to control. And but ultimately, what you want to do is to want it to be able to deliver, for example, an apple to your hand. So be very accurate when it comes to positions. So the question is, how can we actuate, or which angles do we have to set for all of these chambers here? So all of these actuators, what angle do we have to set in order to make it get to a certain location? That again is something that we can learn using machine learning. And so that's what's done here in this video. So let me just explain this. So what you see here is motion capture cameras. And with these motion capture cameras, they first recorded all sorts of movements of the robot, and they also recorded where the robot hand ultimately was at the end. And then they learn a mapping between where we have to go and what joint angles they have to set. And once they have learned this mapping, they can use that in order to control the robot. I can just show you here. So let me see here at the end. So basically, the person is moving around and holding this cube that the robot is trying to follow. And you can see that the robot even extends in order to get there. All of this behavior that you see here was just autonomously learned. The robot was just moving around in the beginning. It was collecting data. And from that data, it learned a mapping between the final position and what the joint angles have to be. Okay, so that was robot control, which is, as I said, what typically people understand under machine learning for robotics or robot learning. Another thing is robot state estimation, or just generally state estimation. I'll actually skip the slide and immediately get to a video, which is a little bit more interesting. So in this video, you see a person playing table tennis against a robot. So you see here, a person is playing table tennis against a robot. So there we are. So that's pretty cool. But what the robot needs to do here is to estimate the state of the human at all times. Why do we have to do that? Well, it turns out if the robot were to just wait for the ball to come to the other side, then using its camera, it would be able to detect the ball. But by the time the robot goes to the position of the ball, the ball already zoomed through, because table tennis balls are very fast. So even with a high frequency camera, you can detect them. They have a high velocity. So getting the robot there in time is virtually impossible if you're waiting for it too much. So what the robot needs to do is to anticipate, to model the state of the human. Is the human going to play a forehand or a backhand or a smash, or what kind of attack is the human going to play? And so at this time, the robot already has an estimate of whether the human is going to play forehand or backhand. And so what the robot can do as a result of that is to already go to the right location and then just kind of improve the final, or get the final inches right to really hit the ball. Okay, so that's what we mean by state estimation, trying to estimate the state of either a human partner or the environment or itself. And that's actually a pretty big thing, because ultimately one of the big hallmarks of robotics is for humans and robots to work together, you know, like a co-worker robot or a robot that's in your kitchen, kind of from time to time hands over something to you. And so for that, the robots can't just rely on their sensors. They actually have to actively model the state and anticipate the future. So just reacting to something is not enough. Okay, so that's one thing we can do with machine learning. Another thing we can do is learning metrics and conditions. So with that, what does that really mean? Well, one of the big concepts in robotics and control in general is this concept of an optimal action. So in some states, some actions are optimal, but what that really means is, for example, you have to define that, for example, as you're driving, kind of an optimal action is to stay on the lane and not hit anyone. And a suboptimal action is maybe getting out of the lane. And even more suboptimal action is getting out of the lane and hitting something. And so what robotics is often about is finding an optimal action. But in order to define what optimal is, we need to have some idea of what does it really mean optimal. And what's this idea of a utility or a reward? So we need to have some function that tells us, well, if you do this, that's good. If you do that, that's even better. Or if you do this, that's really bad. Where do these functions come from? Again, normally you as the expert have to write down such a function, such a reward function or utility function. Now, the problem is, imagine someone asks you, let me ask you this question actually immediately. Can you write down a utility function, a reward function that tells me how a spider walks. Basically, it should give high values if the movement looks like a proper spider movement, and it should give low values if the movement that we observe is not the movement of a spider. Well, maybe you can come up with something, but it's kind of awkward. You have to kind of turn this intuitive concept of motion and spider and proper spider motion, you have to turn that into equations and integrals and stuff. Yeah, that's not easy, even for experts. And so the question is, instead of hand coding such utility functions that tell us choose A and not B, can we maybe learn such a utility function that just kind of from a couple of demonstrations figures out, oh, these actions are better than those. And here I'll give you an example from autonomous driving. So let's say we would, we ask people to drive around in a simulator. And well, we ask some people who are very aggressive drivers. Yeah? So for example, here on the left side, you see aggressive drivers. We ask them to just kind of steer the car, the blue car, and we collect data from these aggressive drivers. And so the aggressive driver, for example, would just kind of immediately take over, and then kind of once they take over another car, they just kind of accelerate. Whereas an evasive driver, when they're taking over, they're basically just kind of trying to steer as far as possible away from another driver. And then finally, at the end, we have a tailgater that tries to, or the tailgaters try to stick around behind other cars. So one thing we can do is we can just collect data from these experts. Instead of asking them for equations, we ask them for data, give us examples. And then from that data, we can learn a utility function. By the way, kind of just to kind of highlight what this aggressive driving really means, here's an example. So here's an aggressive driver, for example. And the aggressive driver kind of really aggressively goes between the cars and takes over. And yeah, there again, kind of they're just kind of very aggressively driving. Whereas maybe, so this looks like an evasive driver. Evasive driver is trying to steer as far as possible away from others when they're overtaking, and so on. And so once we have these demonstrations, we can turn them into a utility or reward function. And the easiest way for you to imagine it is actually as just some sort of like map that tells us kind of hot and cold. And so here you see an example for that. So let's take the one on the left side. So this is really a map, and kind of you see here two cars again. And the one car that we are actually looking at is the car here, kind of the lower car. And this map now has colors, and reddish colors mean a high reward. So you should go there and kind of go to that position. Whereas blue positions are give us back a low reward, meaning this utility function here just takes every position, every state that the car could be in, and tells us hot or cold. Or you should not be in this state, cold, blue, or hey, you should be in this state, go there. And we can learn such a utility function again from the data. Okay, let me ask the audience. I think there are some questions, but let me ask the audience just generally. The one on the left, which one is that? Evasive, tailgater, or aggressive? So A, B, or C? Evasive, tailgater, or aggressive? Please type that just into the chat if you're still around. What do you think?
You guys can write it into the Q&A as an answer since we don't have a chat.
Oh yeah, okay. Into the Q&A, please. Anyone? So there's a first one saying aggressive, tailgater. There's another aggressive, evasive. The one on the left, yeah, evasive. More people. We have. Anyone else? An idea? Aggressive. Okay. Okay, good. Would anyone want to kind of just speak to me and tell me why they think it's a specific one?
If you guys press the raise hand button, I can let you guys speak if anyone wants to unmute. Or
Yeah,
you
let's
can
have
put
this
your
interactive.
explanation
So
in the chat.
please
Up to
speak
you.
to me. Anyone? The left one, is that aggressive, evasive, or tailgater? Come on, guys and girls. Anyone? There is a question from Kyung Hao. I can answer that later, maybe.
All right,
Anyone with a raised hand? Pranav, please talk to me. Yes.
Yes, so I think it's a tailgater because the tailgaters go behind other cars.
Ah, I see,
and that's the space behind those two cars.
Ah, that's
Yes.
a very interesting kind of, we're talking about the left one, no?
Yeah.
Yeah, so that's a very interesting observation, but I think you have the direction of this maybe kind of slightly mistaken. They're actually looking in this direction, kind of in direction of the left side.
Okay.
And we're looking at the lower car. And so the lower car is trying to get ahead of the other car, the one in the middle. And so basically it's getting to that red zone ahead of the car in the middle, and it's actually an aggressive driver. I think you only had the orientation wrong, but you basically had it like, you basically had it right. It's just like the other orientation, kind of it's in the other way. So the tailgating driver is actually the one that we see on the right side, which kind of overlaps with, I think, what you had in mind originally, because the tailgating driver is like, basically the map looks very similar to the left side. It's just kind of inverted. We have now behind the cars, we have these red spots. Okay, good, cool. Hey, Pranav, that was great. And please talk to me. I think over the next 3 days, we can have some really fun interactions, and there are some really interesting insights to come from these interactions. And by the way, everyone, if you have a question, kind of a deep question that is related to the current slide, then just kind of raise your hand and I'm happy to take it. Okay, so now that we've extracted such a reward function, so a function that basically for every point tells us, oh, this is good, this is bad, we can take the reward function and try to find, automatically try to find a policy that would get us only through the red zones, kind of the high reward zones, and allows us to avoid all of the blue ones, kind of the blue low reward zones. Okay, so that was learning a reward function. Now, let's try out something else. Can we do something else with machine learning? Well, one interesting thing is to learn when to switch, which turns out to be a really important thing for robotics. And so let's say kind of you wanted to pick up with this bimanual robot to pick up something. And so one way to do that is obviously you go from the left side and you go from the right side, and then you pull it up. And whether you start with the left side first or with the right side first doesn't really matter. But for you to kind of pull it up, you have to have both hands on the object. And so those are switching conditions. And so you can look at this as phases, really. So in the first phase, we have the object on the table, and then you can move either the left hand to the object or the right hand to the object. It doesn't really matter. And then once you've done that, you have to move both of the kind of the remaining hand. You have to move that to the box. And only when you've done that, you can transition to the fourth phase. And now the question is, who tells you kind of what these arrows are, kind of when you can transition from phase 2 to phase 3? Now, I'm pretty sure if I were to ask you to do this, you would probably do it with like if conditions. No, I mean, that's what we're all taught in school. Kind of if the robot hand is on the left side and so on and so on. But there are many tasks where that if condition is actually very hard to figure out. For example, for lifting it up, you may actually have to have both of the hands making contact and a certain amount of friction already be established, or kind of a certain amount of pressure, let's put it this way, already being established. And there needs to be a symmetry between the two hands, and so on and so on. So creating this condition is not easy. But what we can do is we can learn a function. We go back to functions. We hear a lot of times today a function. But we can learn a function that tells us that we give the current condition, the current state, and the next state we want to go to. So for example, I'm in phase 2. I want to go to phase 4. Can I do that? And the function tells me yes or no. So you give it the current state and the next state you want to go to, and it tells you, for example, in this case, from phase 2 to phase 4, there is no transition. And if you're in phase 3 and you want to transition to phase 4, so you give it 3 and 4, it would also look at the joint angles, at the pressure, and so on, and then make a determination, can we transition or not? So that's the idea of learning conditions. And I hope what you're seeing today is like, machine learning for robotics is not a single thing. It's like many things. One of the big topics in machine learning in general is perception, computer vision. And so, well, in computer vision, one of the main tasks is actually detecting objects, for example, detecting apples, and maybe counting apples. And of course, also segmenting objects out. So for example, for a robot to grasp an apple, it needs to know what is the apple and what's the background. You know, we need to do a kind of a foreground background segmentation. And if you only have a single apple on a table, that's maybe easy. But if you have many apples kind of next to each other, then this sort of segmentation, what you see here in the pictures, can become really tricky. Right? And so here in the pictures, for example, we see a bunch of apples. And then what we're trying to segment by colorizing this picture is to figure out what are individual apples in there. Now, you could implement this by yourself. There are actually segmentation algorithms, but it turns out that with these segmentation algorithms, many times they can easily be fooled. So for example, if you have something that has like a certain texture that looks like the background, you know, then they can like these segmentation algorithms can be fooled. If you have something that has, for example, only edges and doesn't really have like some interesting kind of shape in between or texture in between, then it's very hard to segment it out. Now the question is, can the robot learn such segmentation and to improve the segmentation by itself? And so that's an experiment that we did a while ago at my lab. And the idea was the following. Imagine you have a robot, and that's what you see there. You have a robot and it has this beacon. There's like a short stick protruding coming out. And with this beacon, it kind of touches objects in the environment. And in the beginning, it only kind of sees kind of a picture from the camera. And to the robot, the picture of the camera makes no sense. It doesn't know what is an object and what's not an object. So, for example, the robot may be seeing a scene like this, and the true segmentation of this scene into objects would be, well, black is the background, is kind of the floor, and then, or the table actually, and then kind of we have this pink stuff, which is kind of here this basket, and then we have these kind of 3 other colors, blue, yellow, and green. Those are the boxes. And so if we overlay the segmentation over the scene, we get really nicely carved out objects. Of course, this is what we know is the true segmentation. The robot doesn't know that. And so maybe in the beginning, the robot tries to create such a segmentation thinking, well, everything in blue is one object and everything in green is another object. Another segmentation would be something like this here, where things, everything in yellow is one object and green is one object and blue is one object and pink is one, and so on. Or another segmentation could be, well, everything is just a single object. Everything is just blue. In the beginning, the robot has no idea, kind of, are these all just lumped together, one object, or are they individual objects? But what the robot could do is to just touch them, you know? So in the beginning, the robot kind of doesn't know anything, and then it touches them. And so some objects move together, whereas other objects or other pixels, let's put it this way, some pixels move together and other pixels don't move together. All the pixels that move together, we kind of know if they move together, that's probably they belong to the same object. And so in the first time the robot does this, it can now have a better hypothesis about what pixels belong to the same object. And it does this again, and now it has an even more refined estimate of what pixels belong to the same object. And as you can see, over time, after 15 actions, after 15 prods of the environment, the robot has a pretty good idea of, well, what the true segmentation is. Here's another video of that, kind of highlighting how this could look like in action. So the robot is just prodding this object, and it's trying to figure out how is the object structured, and how do the individual pieces belong together. And so here, for example, it's touching the object and it's tracking pixels. Some pixels are moving together, others are not moving together. And then it's using that in order to figure out the structure, the individual elements of this object. So for example, it figured out the yellow pixels move together, that's one object. The pink ones move together, that's another object. And the blue ones move together, that's yet another object. And so this is called interactive perception or interactive computer vision. You don't just collect a data set and kind of do your magic. You have the robot actively collect the right data set, the data set that it really needs. And you are not even kind of as a human expert, you're not involved in this process at all. Okay, and so, yeah, we still have 10 minutes, that's good. So let me just briefly go over machine learning for control architectures, because this topic, honestly, you don't find it too often out there. But just kind of at a high level, let me just kind of visualize it using a picture. What we often do in robotics is what we call behavior-based robotics. So you have a bunch of sensors giving data to the robot. So the sensors are typically the cameras, IMUs, pressure sensors, and so on. And then we, as experts, we implement certain behaviors. For example, if you want to implement a humanoid robot, then the humanoid robot needs to be able to walk, needs to be able to grasp, needs to be able to lift some object, for example, maybe to kind of climb upstairs, and so on and so on. So you have these individual behaviors, and these individual behaviors need to be somehow combined together to create the continuous motion of the robot that maybe first walks and then steps up the stairs and then picks up an object and so on. And then that's called arbitration. It's like a referee that says, hey, now I have to avoid an obstacle, kind of you go. And then kind of now it says, oh, I have to climb upstairs. Okay, behavior for climbing upstairs, you go. Maybe now it says, I have to walk, and while I'm walking, I need to pick up an object. And then it says, walking and picking up the object, both of you are active. That's called arbitration in behavior-based robotics. Now, the problem is arbitration, let's move on. Actually, we don't really need to see this here. Arbitration comes with some pitfalls. And so imagine, for example, you have two modules or two behaviors that are controlling the robot. And one is saying, the obstacle avoidance one is saying, hey, avoid this obstacle that's in front of us. And then you have another behavior, the go-to behavior or kind of go-to-goal behavior is saying, hey, I need to go to the goal. So one is going to the left and one's going to the right. And we need to arbitrate or kind of combine the two. So what do you think would happen in this scenario? Who would win, or what's probably going to happen? Anyone an idea? In this scenario, kind of raise your hand or just kind of type something in here. I'll see it. Anyone? Any idea? What's probably going to happen? So one behavior is saying go to the left. The other one is going to saying go to the right. So is it going to go to the left or to the right? What do you think? Or maybe yet another thing. Svea?
Yeah, maybe it's going to the right because there is a goal that it is assigned to.
Close, but unfortunately not exactly correct. So actually, maybe if you would have implemented it, it would have done that. But actually, the most common implementations would not lead to that. Anyone else? King Hao, Chen are saying to the right. That's not it. So who's for left? Anyone for left? Actually, this is kind of a tricky question. It is a tricky question, by the way. So Svea, like, that was good. Like, you're saying the right things. It's just like, unfortunately, the way we implement our robots is really bad. So like, this is not speaking for roboticists right now. So who says it would be going to the left? No one? Everyone is saying it would be going to the left. So here's the thing. It would not go to the left and it would not go to the right. It would go straight forward, because the way a lot of these arbiters are implemented is as a vector addition, basically kind of the average of the two vectors. So instead of, so in this scenario where basically one behavior is saying go to the left and the other one is going to the right. So you have these vectors, one is showing to the left, one is showing to the right. And when you sum them up and kind of average them out as a result, you end up with a vector that shows straight forward. And so instead of actually solving it, or like even in a suboptimal way of like avoiding the obstacle and kind of taking a longer route, you actually head straight for the obstacle. And that is a big problem in robotics. Now, of course, some of you may be saying, well, in practice, that doesn't really happen. Let me show you a video so I can change your mind. So this is from the largest autonomous driving competition. So the Urban Challenge. And this is basically where all of the autonomous driving kind of technology came from. It came from this competition. So this was a DARPA-led competition. And here you see the car from my former university, my alma mater, Georgia Tech. And exactly this happened. Kind of, it was not able to decide, go left, go right, boom, it just headed for the exit, you could say, and then just crashed. Okay, so one thing we can do with machine learning here is to actually arbitrate between these behaviors using machine learning. And so that's an algorithm that was proposed called DAM. I'm not kind of using curse words here. It's the name of the algorithm. It's called Distributed Architecture for Mobile Navigation. And the underlying idea is to have a neural network learn when to and how to combine different behaviors together in order to avoid these kind of situations. And also to be able to adapt it to whatever environment we're using this in. Okay, and with that, I come slowly to the end of my talk. But this part, just stick around. This is the coolest part, I promise, like, it's the coolest thing ever. And it has to do with the body, the role of the body of the robot. So many times we kind of buy a robot, like even in universities, we do that. We buy, a robot from Boston Dynamics or one of these hardware manufacturers. And then we try to program it and bring the intelligence in using software. But actually a lot of the intelligence is in the hardware itself and the way you build the robot. And so here, for example, we see what's called the passive walker. What you see there is nothing but two pieces of metal attached to kind of this curved piece of plastic, basically at the bottom. And then when you kind of put it on a ramp, it will just walk down. And that happens automatically as a result of basically gravity pulling it down, and then gravity being kind of turned into kind of a force or moment in the kind of perpendicular direction. And that leads the robot to basically, basically just walk. And keep in mind, this robot has no actuation device. It does not have a motor, and it's not active in any way. It's like just, that's why it's called passive. Like we don't have an energy device, that we don't have a battery or something that actually actuates this. So we don't have a motor, we don't have a battery, and it still moves. And all of that is just because of the intelligence of how to design this. And of course the task. If you just put it on flat ground, it doesn't work anymore. And so the idea behind using machine learning for robotics is, can we create robots whose bodies already solve part of the task? So kind of figure out the intelligence of the body. And here's a really cool video that shows you this. So these here are evolved creatures, or evolved robots, you could say, that are automatically generated to solve a task. So in this case here, we just randomly create different robot morphologies, different shapes, and then have them in a simulation try to swim effectively. And then we take all of those that get far and then have them basically get children, recombine the DNA. And over time, we get some really interesting looking animals, artificial creatures that can swim really nicely. Here's the same thing for a different task where they now have to walk on ground. Again, we just randomly create shapes and then have them, the good ones, the ones that locomote and move forward, have them have children. And over time, they actually kind of move forward really nicely. And what I like about this video is it's also very lifelike. It's some of these creatures look really out of some movie or so. Really interesting shapes and kind of setups. So let's just quickly move forward. So here in this case here, we see different shapes that also are trained in such a way as to go to a certain location. This here actually looks like a small frog trying to kind of swim to this red dot. And here you can see that the generated morphologies are really interesting in that some of them look like a ship that is steering, or like some sort of U-boat or something. Another thing we can do with this is to actually have them compete against each other, like some sort of arms race. So in this case here, we have two different agents, two different robots, and they have to get to the green box as fast as possible. And so each one of them is basically changing its shape so as to solve this task and get to the green box faster than the other. Now, of course, you look at this and say, well, all of this is like simulation. But actually, one thing you can do nowadays with 3D printers is to take the simulation, kind of the simulated robot, or the robot that you just generated in computer. You can take that and then effectively just print it. And that's one of the things that was done actually about like 10 years ago by a researcher at Cornell. And so what he did is to have the simulation where they created all sorts of kind of weirdly shaped robots. And they also used the compute power of PlayStations all over the world in order to create different shapes and behaviors for these robots. So literally, they went out and asked people who have a PlayStation, hey, can you please install this program? And the program will, in the back of the PlayStation, without you really noticing it, it will create these different morphologies and try to find one where the robot moves forward a lot. And once it finds something, it sends it back to the station, kind of the central station at Cornell University, where the robot eventually then gets printed out using a 3D printer. And then kind of once it's printed out, they can actually try it out in the real world. So let me show you that process. So here's the printing process of the for the robot. And once you have it printed out, you can try it out in the real world. So this is one of the morphologies. You can see here how it's moving forward. And so all of this came from simulation. And here's yet another morphology. Okay, so we are at the end of my talk. I tried to stick to the time limit so that Alper doesn't get mad at me. So we still have 2 sessions to go, but I hope I got your excitement up and running. What is it good for? Everything we've learned so far? Well, absolutely nothing you could say, or everything. It's kind of really to get you excited. And then the details, how do you realize this? That's something that we're going to be talking about in the next lectures. So today, we talked about the what, learning for controlling the robot, learning for perception, how the robot sees the world, learning for state estimation, for estimating the state of a human, for example, and so on, up to morphologies, learning how to create differently, weirdly shaped robots. And tomorrow and the day after, we're going to be talking about evolutionary algorithms and neural networks, which are specific methods that allow you to do the things you just saw by yourself. And yeah, I hope that was interesting for you. I'm happy to take any questions that you have either in the chat or if you raise your hand. So yeah, thank you all so much.
Thank you so much, Henny. We really appreciate all the time you spent with us today and all the time you will be spending with us for the next 2 days. So we have a couple questions in the chat. Did you want to read them, or do you want me to read them?
Okay. No, I can take them. So what books are good for beginners that are going into machine learning? What resources would you recommend for experts? So this is a really good question, and it's not an easy one. So there are multiple like books on machine learning, and many of them are actually very mathy and kind of on the theoretical side. So I'll pick maybe 2 books and show them tomorrow that I think are good books for, I wouldn't necessarily say for complete beginners, but for people with a little bit of math background and coding background. So I'll be talking about, I can talk about that tomorrow, and maybe also suggest something for experts. Unfortunately, to this day, we don't have really a book on robot learning. That's actually something that at some moment I wanted to do myself, but I didn't really, I never really got into it. So meaning what we have is books about robotics, motion, and so on, and books about machine learning, and then also books about AI, which cover some of these other topics. But we don't really have something that covers all of this from the point of view of robot learning. So how do we actually connect hardware sensors, like actuator sensors, and kind of control algorithms with machine learning, and kind of everything that you just saw, for example, from my presentation is not something that you would pick up in any one book that you would find out there. So that's an unfortunate thing. But yeah, I'll be talking tomorrow again about some books that I could recommend. Okay, the next question is, can we consider the style-based inverse kinematics approach to train the robot similar to the approaches employed in training for autonomous driving vehicles to handle different scenarios and situations? So please correct me if I'm wrong, but basically the question is whether we can use similar approaches for style-based inverse kinematics and for autonomous driving. In fact, yes. So a lot of that goes back to this entire field of imitation learning, learning from some data that was provided by a human. So there's an entire field of literature on imitation learning. There are different ways of how you can do imitation learning. And you can see style-based inverse kinematics as one type of imitation learning, where we basically collect motion data from humans and we do imitation learning on motion data. What we saw earlier, I gave the example with the autonomous driving, is technically also something like that. We collected data, motion data from humans, but what we learned was something different. We learned utility function, something that tells us good or bad. So in style-based inverse kinematics, we learned a function that spits out joint angles. Yeah, kind of takes in position and spits out joint angles. In the autonomous driving scenario, we learn something that tells us bad or good, and so on and so on. So basically, they go back to the same theory, but these are two different things that we've learned there. But it's great to see that you can actually, like through your prism, you figured out that these two are connected, and so that's absolutely correct. So let's go back. Do I have to be an expert in physics or engineering to dive into this field? No, you can. And so that's one of the big goals actually also, like for me today, to teach you, you can get into this basically right now. It's always good to, if you need it, be able to kind of understand basic math and like physics and a little bit of engineering, but you don't necessarily need it. And I think the most important thing that you need here is perseverance, that you stick to it. Kind of you are really interested in it. Like, you know, when I first saw some of these videos here and kind of was a student myself, I got so hooked up on this. Like I couldn't stop, like day and night. I would be coding things and like trying things myself, just drawing things out. And a lot of that was just nonsense. Like, but I learned from that. And so I think what I'm trying to say is stick to it. It's time that you have to invest. You don't have to be an expert in either physics or engineering. So, and then let's see here. There are open questions. If my understanding is correct, some of the applications you have shown were primarily based on imitation learning. Oh, that's good, yeah. What do you think about causal inference and causal reasoning in robotic application? Hey, that's an amazing question. So maybe you should just join my lab. So I'm all about causal reasoning, and actually that's something that I'm dabbling into right now. So for everyone else who doesn't necessarily understand the question, really think of it of like from the point of view of cause and effect. So a robot could learn to deal with the world if it learns that, well, if I do this, it will cause this effect in the world. And if I do something else, it will cause another effect. And if a robot were to be able to model this and learn this causal relationships between its actions and the effects of those actions on the world, it would be able to know, well, what should I do in order to achieve a certain effect? You know what I mean? For example, the robot could think about, well, how can I get a box on the table? And it knows if I lift the box and kind of put it over there, it would get there. It kind of knows the relationship between its own actions and the effects these actions have in the real world. So it's a very big topic and it's a very interesting topic. Unfortunately, it's also a very tricky topic. So causal reasoning has been around for quite a while. And it's actually a big kind of thing, you could say, in modeling kind of user behavior, for example, on the internet. But there are some aspects that make it hard. For example, people or experts have not yet agreed really on what causality actually means. What does causal really mean? There are like long debates about that. What does it really mean to cause something? Or is it just correlation? Like these two things happen just because they happened at the same time. And so that's one of the things kind of there, but it's an ongoing research topic. And some of that stuff we do in my lab. So basically what I'm saying here is it's a great topic. It's a little bit challenging, more at the PhD level. So maybe you want to join my lab and then kind of we can get all of this sorted out. So then there is May, who's also asking, serving coffee sounds like a hard task. How did people work on making the robots that serve coffee? Well. A lot of that is fake, unfortunately. So of course you can always program the robot to pick a very specific coffee mug or coffee cup and bring it to a very specific location or hand it over in a very specific way. You know, you can always hack it. You know? But then let's say the mug, the shape of the mug changes. Now the robot needs to grasp it differently. And I'm pretty sure those demos that you're referring to, they would immediately fail, immediately, if you give it a different cup. Potentially, even if you pour too much into the mug or cup, it would already fail. And then, for example, if you would tell it to walk on over like uneven ground to get to the goal, it may also fail. And even if it gets to the goal, and then it has to hand the mug to a human user. And the human user, for example, has his or her right arm unfortunately broken, you know, someone with an impairment, physical impairment, and the robot kind of needs to hand it over to the left arm. The robot wouldn't be able to even realize that. So that goes back to perception and state estimation, estimating the state of the human. And that's something that we humans are pretty good at. If you see someone who has, you know, like some sort of cast or some other device that kind of indicates that they're currently physically impaired, that you can, then you understand that and you change and adapt your actions to that. Robots would have no idea how to deal with it. So I think what I'm trying to say here is a lot of that is really fake. And that's one of the main reasons why you don't see robots in the kind of in restaurants and kind of all of the restoration industry. You don't see them there. There's a lot of effort to get them there, but no company in their right mind would now try to replace, for example, the kind of the serving staff with the robots. I mean, you can try, but you're probably going to fail. And the reason for that is those are very unstructured environments. People are very tricky to predict, especially customers. They're probably sometimes grumpy, and sometimes, again, they have these physical impairments, or they have a child, and so on and so on. Robots would not be able to adapt to that. So I think that was it with regards to all of the questions. Thank you all so much for the kind words. Oh, Luke has a question. Do you think robot learning is more of a long-term research type than an immediate employment type? Ha, okay. So this is here kind of a word of caution. Even though I basically say that there are things that still have to be resolved, that doesn't mean that this field is not an interesting one or one where you should not seek employment. You should definitely seek employment in this field. It's the highest paying field in kind of all of computer science right now. If you do anything with machine learning and robotics right now, you're basically at the top of the food chain. But of course, you shouldn't be doing it for money. But if you look at it from the employment and employmentability point of view, if you have this shared background in machine learning and robotics, you're pretty much at the top of the food chain when it comes to hiring. And I can tell you from my students, the hiring packages that they get, they like from time to time, I'm thinking, hey, maybe I should leave academia altogether because they get like triple my salary with a signing bonus and so on and so on. So you should definitely do it. And not only for that, it's also really fun, you know, like you can create these creatures and become like the next Disney, create like some sort of like animated creature or robot, and you can see it then behaving and interacting with you. That's really fun. But there are some challenges that can be solved using robot learning in the immediate short term, and then others that are long term. And unfortunately, we hear mostly about the things that are more long term. For example, like barista, coffee robots, and so on. I think that's going to take a while. But there are other things like, for example, you know, inspecting a nuclear power plant. Well, humans can't do that anyways. Like you wouldn't want to send a human to Fukushima. So it would make sense to have specialized robots with adaptive capabilities that can actually locomote, manipulate, and kind of remove some of the debris in Fukushima. And that's true for a lot of like the more industrial applications. So I think one way to go about this is to just make our current industrial robots smarter, more adaptive, cheaper as a result. That's probably, there's a lot of really interesting stuff happening in that field, and potentially also getting robots a little bit into the medical field, you know, robots that help with hip replacement and so on. I think that's where the short-term gain is. The stuff with robots, you know, autonomous driving and so on, even though there have been some substantial gains made, that's going to be taking a little bit longer. And robots in your home are going to take a long, long time. Of course, I mean, if we're talking about robots that are like toys, you can have them tomorrow. But robots that actually do anything interesting in your home, that's going to take at least 10, 20 years. Thank you all so much. That was great. I enjoyed it. And yeah, we have 2 more days to go. So yeah, talk to you tomorrow. Thank you, Alper.
Thank you so much, Henny, again, for spending all your time with us. On behalf of Labs, we really appreciate it.
My pleasure. This was fun. And yeah, see you tomorrow then.
Have a great day, everyone.
See you then. Bye.